In this video, we're going to talk about surds. We are going to look at a lot of examples that will help us really understand how to solve surd problems. But before we do that, let's define what is surds. Surds are irrational roots. What this means is that a surd is simply a number that is irrational and is both a root. For a number to be irrational, we cannot express it as a whole number or fraction. So for example, if I have something like square root of 2, if I punch this in my calculator, I'll get something of 1.414 and then continuous. There are numbers after this. So I cannot write this as a whole number or fraction. This is a decimal number. But if I have something like square root of 25, now square root of 25 is simply equal to 5. Now notice that both numbers I said here, root 2 and root 25 are root. But one of them cannot be expressed as a whole number or fraction, which is root 2. Cannot be expressed as a whole number. But root 25 is expressed as a whole number. So root 25 is not a surd, while root 2 is a surd. So you need your number to be in a root. I need your number to not be able to be expressed as a whole number or fraction. To show you extra examples of surds and non-surds, if you have something like root 5 and root 16, root 5 cannot be expressed as a whole number, but root 16 is equal to 4. So this is a surd, while this is not a surd. Okay? This is simply how to identify a surd and a non-surd number. Let's jump into examples so that we'll learn how to solve surds. So one of the first things you need to learn when learning how to solve surds is to simplify them. So we have some examples on the screen. I would simply write solution here. For the first example, we are told to simplify root 96. So I write here root 96. If you want to simplify surds, you need to be able to break down this number into a perfect square. What do I mean by a perfect square? Now, if you have something to say 2 square is equal to 4. 4 is a perfect square number. You have 3 square is equal to 9. 9 is a perfect square number. You have 4 square is equal to 16. 16 is a perfect square number. 5 square is equal to 25. 25 is a perfect square number. So numbers that have a root, which is a whole number, is a perfect square. Now in this case, you have 6 square still here, which is like 6, 7 square, 49, like that. So you need to be able to find these numbers inside your root. So this is equal to, now for 96, what perfect square can go into 96? If you use your calculator and check 96 against all these numbers, you notice that 16 can go into 96, and it happens 6 times. So I write this 96 here as 16 times 6. Here we can separate these roots here. So whenever you have something like a times b on a surd, you can rewrite it as square root of a separately times square root of b separately. Here we can still do the same thing and say root 16 times root 6. So that this will be equal to root 16 is 4 times root 6. So since we cannot simplify this further, we rewrite it here. So this will be root 6. And this is the simplified form of root 96. Let's quickly jump into the next example. So for the next example, we are told to simplify root 20. For root 20, we can break it down. So the perfect square that can go into root 20 is 4. We can say this is 4 times 5, right? So we have 4 times 5. This is still equal to root 4 times root 5. This will be equal to root 4 is 2. Root 5 cannot be seen 5 for that. It is a surd. So we write it out as root 5 here. So this is the answer for simplifying root 20. Let me clean up space. So for the next example, I thought simplify roots 1 to 5. You can pause the video and try to solve this one yourself. So like we did before, we try to look for a perfect square inside 1 to 5. The perfect square that can go into this is root 25. So if we break 1 to 5 down, we can have 25 times 5. From here, we can separate it and say root 25 times root 5. So that this is equal to root 25 is 5. So this is 5 square root of 5. That's it for roots 1 to 5. Then for next example, we have root 99. We should break this down. It becomes square root of 9 times 11. So that this is equal to square root of 9 here times square root of 11. And then here we have square root of 9 is 3 times square root of 11. This is a surd, so we leave it at this. For the last example, we are told to simplify root 12. So this is root 12. The perfect square that can go into root 12 is 4. So we write this as square root of 12 is equal to square root of 4 times 3. This is equal to square root of 4 times square root of 3. This is then equal to square root of 4 is 2. Square root of 3 is square root of 3 here. So that's how to simplify surds for a basic level. We're going to look at more examples, but let's look into how to add and subtract surds. In order to add and subtract surds, there is a key idea you need to have in your mind. Say you have a surd of root 2 plus root 2. You can add these two surds because they have the same roots. So here root 2 plus root 2 will be 2 root 2. If you have 2 root 2 plus 3 root 2, you can also add these two surds because they have the same root number here. So it will be saying 2 plus 3, which is 5. So your answer will end up being 5 root 2. But if you have something like root 2 plus root 3, you cannot add these two surds because they do not have the same roots. So the answer here will ultimately be equal to root 2 plus root 3. The same thing goes for subtraction. You can subtract the surds here. You can add the surds here, but you cannot subtract the surd here. So if you have root 2 minus root 3, this will be equal to root 2 minus root 3. Now that we know this, we are fully prepared to solve our questions. So I'll clean up this space here. The first example, we are told to solve root 2 plus 2 root 2. So this is simple. We look at the roots. The roots here is root 2 and root 2. We can simply add this up. The supposed number here is 1. We assume it to be 1 if there's no number here. So since they have the same roots, we can safely add this number here with this number here. So we'll be saying 1 plus 2, which is 3. So we have 3 roots 2. That's it for the first example. For the second example, we have 7 roots 3 minus 2 roots 3. So this will be 7 minus 2 is 5. We have 5 roots 3. For the next example, we are told to do root 98 minus root 8. Now, if you notice something, the roots do not have the same number, but we can simplify these roots further. So how do we simplify these roots? We try to look for the perfect squares inside each of them to simplify them to their smallest forms. Now, if you look at root 98, the perfect square inside root 98 is 49. So that this can be written as 49 times 2. Now that we've broken this down into a smaller form, we can do the same for root 8. So this will become minus root. The perfect square inside 8 is 4. So we can write this as 4 times 2. If we simplify this, this looks like square root of 49 times square root of 2. Now bracket this so that we don't confuse it with this part. This will be minus. We break this down to bracket it. So we have root 4 times root 2. From here, we have this as equal to root 49 is 7. Root 2 is still there. Minus root 4 is 2. Root 2 is still there. So if you notice, we now have the same surds for each of the number. So we can safely subtract now. You have 7 here, they have 2 here. This is 7 minus 2, which is equal to 5 root 2. So that's it for question number 3. For question number 4 and 5, you can pause the video and try to solve it yourself. For question number 4 and 5, we are simply going to be doing the same thing. We have 5 root 3 here minus root 27 plus root 48. Okay, so if you notice, the base numbers are not the same, but we can simplify this and this. So this is 5 root 3 minus root 27 can be simplified into root 3 times 9 plus root 48 can be simplified into 16 times 3. So that this is equal to 5 root 3. If you break this down, it looks like root 3 times root 9 plus, if you break this down, it looks like root 16 times root 3. So that this is equal to 5 root 3 minus, here we have root 3, root 9 is 3 times 3, so this is 3 root 3 plus root 14 is 4 times 3, so this is 4 root 3. We have 5 root 3 minus 3 root 3 plus 4 root 3. It ultimately is 5 minus 3, which is 2, plus 4, which is 6. So this is 6 root 3. So that's it for number 4. Let's jump into number 5 and finish the analysis. I'll put enough space here. For number 5, we're told to do the addition of 5 root 45 plus root 20. So if you look at this, again, the roots are not the same, but we can simplify them. So if I simplify this, this looks like 5 roots. Now 45 can be broken down into smaller terms of 9 times 5 plus root 20 can be broken down into 4 times 5. Remember, perfect squares are key numbers they're looking out for when breaking down. So this is equal to 5. If you break this down, it looks like root 9 times root 5 plus, here this is root 4 times root 5. So that this is 5, open brackets, we have root 9, which is 3, times root 5 plus, this is root 4, which is 2, times root 5. So we have root 5 here. And then here we have 5 times 3 root 5. So this 5 multiplying this 3. Okay. So 5 times 3 is 15 root 5 here plus 4 root 5. Then I can safely add my numbers here against each other. So that this is 15 plus 4, which is 19 root 5. I'm going to add an extra example. As an extra example, say we are asked to do root 2 plus 5 root 3 minus 6 root 2 plus 4 root 3. So in this case, if you are going to solve this kind of problem, you have different types of surds. Another thing again you need to take note of is that we cannot simplify these surds further down. So one of the key things you do when they are in their simplest form is to put the like surds together. So this one, this are like, this and this are like. So I'll pull in surds with root 2 together first. So this will be root 2, and then this is here. This will now be minus 6 root 2. So it's be like collecting like things. Plus, I'll be pulling this one. So this will be 5 root 3 plus 4 root 3. Then I can now do the simplification. Here's 1. So this is 1 minus 6. 1 minus 6 is minus 5 root 2 plus This is 5 and 4. So 5 plus 4 is 9 root 3. From here, I cannot simplify the surds further, and the surds don't have the same roots. So this is my final answer. If you're dealing with surds, you're going to be solving a lot of multiplication problems. So let's quickly look at multiplication of surds. So we already have examples on the screen. Before we solve any example on surds, there are simple surd rules you have to know when dealing with multiplication of surds. One of the first rules is that if you have a surd, say roots 2 times roots 2, if you have two surds multiplying themselves, the thing you're doing is that you're multiplying the numbers inside of the roots. So this will be equal to 2 times 2. Sometimes we often see this as roots a times roots a is equal to roots a times a. Another thing you're doing is that if you're multiplying a number, say 2 times root 2, because the number doesn't have a root, it is going to be equal to 2 root 2. You can see this as, say, a times root a. This will simply be equal to a root a. If you're multiplying the same surds, like say in this case where we're doing root 2 times root 2, and then we get root 2 square. This will be 2 square inside. This can cancel out this. This will be equal to 2. What this simply tells us is that if you're multiplying the same surds of root a times root a, you are going to get roots a square, and then this will be equal to a. If you're multiplying something like root a times root b, your answer will be equal to square root of a times b, which is ab. And then finally, if you have a number multiplying a surd, you get something of the nature of a root b. These are the key surd rules you consider when you're multiplying surds. Let me clean up space and then let's jump into these examples. So solution, the first example we are told to do is to solve root 2 times root 2. Root 2 times root 2 is simply equal to square root of 2 times 2. Square root of 2 times 2 is square root of 4, and that is ultimately equal to 2. So this is another problem. We are told to find root 2 times root 50. Now you can pause the video and try to do all of them yourself. But let's continue. So this is roots. You multiply the numbers inside. This will be 2 times 50. 2 times 50 is square root of 100. Square root of 100 is 10. For another example, we are told to find roots 3 times root 15. So root 3 times root 15 is equal to 45. This is equal to, we can break 45 down into a perfect square. So we can rewrite this as saying root 9 times 5. If you have 9 times 5, you can separate it and say this is root 9 times root 5. Root 9 is simply 3, so this will be 3 root 5. For the fourth example, we are given a bracket form. So this is root 5, open bracket, root 5 minus 5 root 3. We simply do this the way we do normal algebra multiplication. So this will be this multiplied by this first, this multiplied by this second. First thing we say is root 5 times root 5. So I'll say root 5 times 5. And then minus, the next one will be root 5 times 5 root 3. So if we do all of this, if we say root 5 times root 5, the answer is 5 minus root 5 times 5 root 3. So remember, the roots will be multiplying against the root. So root 5 times root 3 is root 15. So I have 5 root 15 here. We cannot break this number down, so this is the final answer. Let's clean up space before we solve the last example. So for the last example, we are told to do 2 plus root 2 and then times 3 plus root 2. So if you're dealing with two brackets, you do it the way you do regular multiplications in algebra when you're multiplying two brackets. So first of all, we use this bracket to multiply this bracket. That will be 2 open bracket 3 plus root 2. They'll pick the second number here. This will be plus root 2 open brackets 3 plus root 2. This is equal to, by the way. So we say 2 times 3 is equal to 6. 2 times root 2 here is equal to 2 root 2 plus root 2 times 3 is equal to 3 root 2 plus root 2 times root 2 is equal to root 4. From here, we can say this is equal to 6 plus 2 root 2 plus 2 is 5 root 2 plus root 4 is simply 2. So this is 2. And then we have this as equal to, we pull the numbers together and the surds together. So this will be 6 plus 2, which is, and then plus 5 root 2. This would then be equal to 6 plus 2 is 8 plus 5 root 2, still 5 root 2. So that's the answer to this problem. So that's how to multiply surds. If you're going to the multiplication of surds, these are simple examples, but with these examples, you should be able to solve more complicated problems. Now let's look into extra examples on surds in terms of division. So we are going to look at division of surds. So if you're going to be dealing with division of surds, there are some key surd rules that you should be aware of. For example, if I have a surd, so root A over root B, I can rewrite this just like in the multiplication case. I can write this with one root, so it become A over B. If I have this, I can also do this. So we already have some examples on screen. I would come here and write solution. For the first example, we are told to find root 30 over root 5. Let me clean up space here. So if we are doing root 30 over root 5, one of the things we can do is to pull it together. So we can say this is the roots of 30 over 5. So 30 divided by 5 is equal to 6. So this is root 6. This is your final answer. We can also do it for number 2. For number 2, you're told to find roots 100 over roots 4. So we can still do the same thing for this example. You can pull it together and say roots 100 over 4. This is equal to 100 divided by 4 is 25. So we have root 25. Now, square root of 25 is simply equal to. That way we could have done it to say root 100 over root 4. Root 100 is 10. Root 4 is 2. So this is 10 divided by 2 is still 5. You can be flexible with these rules. You can do it whatever way you like, but make sure you are following the right rules. Okay? Now let's look into rationalizing surds, because you're going to have to do a lot of rationalization of surds as you go on. Before we talk about rationalizing surds, there is something I want you to know about rationalization. So rationalizing simply means to remove a surd from a denominator. If we have 2 over root 2, and you're told to rationalize this number, that means you have to remove this surd from the denominator. If you have 5 over 5 minus root 2, and you're told to rationalize this surd, that means you have to remove this surd from the denominator. So let's look at how to do that. For our first example, we are told to rationalize 1 over root 2. So how do we remove the roots from this denominator? A way we can do it is to multiply the numerator and the denominator by this surd. So that will simply be saying this is equal to 1 over root 2. You then multiply the numerator by root 2 and the denominator by root 2. so that this is equal to 1 over root 2 times root 2 is simply 2. And then 1 times root 2 is, you can write it as 1 times root 2. So this is equal to root 2 over 2. So we succeeded in rationalizing this surd here. Let's go into the next example. For the next example, we have 5 over 3 root 2. So I'll be saying this is 5 over 3 root 2. Now, you can use root 2 to multiply the numerator and denominator, or you can just use the whole denominator to multiply the numerator and the denominator. But I'll be using the whole denominator. So this is times 3 root 2 over 3 root 2. If I multiply this and this, I have 15 root 2 divided by, if I have this multiplied by this, I have 3 root 2 square. Okay, so that this is equal to 15 root 2 divided by 3 square times root 2 square here. So that this will be equal to 15 root 2 over 3 square is 9. Root 2 square is 2. So this is 9 times 2. This is equal to 15 root 2 divided by 9 times 2 is 18. From here, I know that 3 can go into this 5 times. 3 can go into this 6 times. So this is equal to 5 root 2 over 6. In this case, since the target was just to eliminate this surd here, we could have just used root 2. So watch another way we could have done this. This is 5 divided by 3 root 2 is equal to 5 divided by 3 root 2. The target is to eliminate root 2. So we can just multiply the numerator and the denominator by root 2. But if we had done that, it should just be 5 root 2 divided by, this is 3 times root 2 times root 2 is still 2 times 2. So this is equal to 5 root 2 divided by 3 times 2 is 6. So most times if you have a number more than 1 and a surd, you can just use the surd to multiply the numerator and the denominator to save you time. Let's look into the next example. So for the third example, we have 2 divided by root 5 minus root 3. Now, if you have this kind of example, you cannot just say root times root 5 minus root 3 for numerator and denominator. You are going to still get a surd. So if you have a denominator where a surd is adding a surd or subtracting a surd, you have to get a conjugate. What do I mean by a conjugate? A conjugate is the number that will cancel out the surd. So let's say you have root a minus root b. If you're looking for a surd that can multiply this surd to give you a non-surd number, you have to use root a plus root b. If you're giving something like root c plus root d, you're looking for a surd that will cancel out this number. You have to use root c minus root d. So you change the sign in the middle. This is the conjugate of this. So we call this ones the conjugates. The conjugates, the conjugates. So the conjugates help us remove the surd from the denominator. Now, in this case, the conjugate is, so write the conjugates of root 5 minus root 3 is root 5 plus root 3. So from here, we can now say 2 over root 5 minus root 3 times, we use the conjugates, so we have root 5 plus root 3 divided by root 5 plus root 3. Let me clean out this space. We can rewrite this as saying 2 open brackets 5 plus root 3 divided by, we have root 5 minus root 3 open brackets root 5 plus root 3. So for the numerator, we can simply multiply everything and say this is 2 times 5, which is 10. This is 2 times root 3, which is plus 2 root 3. Then divided by, if you are dealing with the denominator, you can simply do your multiplication together, but you can also save time. here's how to save time. You can pick this one, root 5 here. So this will be root 5. Then you square it. Then you put a minus sign in between the terms. Then you pick your second term here, root 3. Then you square it. So this will save your time when you're dealing with a denominator. This is equal to 10 plus 2 root 3 divided by root 5 square is this cancels out this, and then we have 5. Root 3 square, this cancels out this. We have minus 3. Another explanation for this is that if you look at these two numbers, they are very much alike and they look like a difference of two squares. So the idea comes from if you have a square minus b square, you can rewrite this as a minus b, a plus b. So if you have this, you can write it as this. If you have this, you can also write it as this. So if you notice, this is a difference of two squares, so we can simply write it like this. So back to what we're saying, this is 10 plus 2 root 3 divided by 5 minus 3 is 2. From here, we can simply use the denominator to divide this one and this one. So we can separate it and say this is equal to 10 divided by 2 plus 2 root 3 divided by 2. So this can break this down to 5. This can break this down to 1. So this is plus root 3. So this is the final answer to our problem. So for our final example, we have 3 root 3 divided by 2 root 3 plus 2. So we are supposed to rationalize this. The first thing we do is find the conjugates here. So the conjugate of 2 root 3 plus 2 is 2 root 3 minus. We use the conjugate to multiply the numerator and the denominator. So this will be 3 root 3 divided by 2 root 3 plus 2 times 2 root 3 minus 2 divided by 2 root 3 minus 2. So that I can come here and say this is equal to 3 root 3 open bracket 2 times root 3 minus 2 divided by, for denominator I have a difference of 2 square. So this will be 2 root 3 plus 2. This will be 2 root 3 minus 2. From here, this will be equal to 3 root 3 times 2 root 3. If I have 3 root 3 times 2 root 3, 2 multiplying 2, that will make it equal to 6. Root 3 we multiply with 3, that will make it root 9. Now root 9 is equal to 3, so this is 6 times 3. So 6 times 3 is 18. So that means here we have 18 minus 3 root 3 times minus 2 is minus 6 root 3. So this is minus 6 root 3 divided by. Now the denominator is a difference of two squares. So what you do is that you pick the first term here. This will be 2 root 3. You square it. Minus the second term here is 2. So you pick the second term and then you square it. So that here you have 18 minus 6 root 3 divided by 2 root 3 square is 4 times 3 minus 2 square is 4. So this is in brackets, and then we have this as equal to 18 minus 6 root 3 divided by 4 times 3 is 12 minus 4. So that we have this as equals 18 minus 6 root 3 divided by 12 minus 4 is 8. So that here we can separate the numerators with the denominator and say this is equal to 18 over 8 minus 6 over 8 root 3. We know that 2 can go here 4 times. We know that 2 can go here 9 times. We know that 2 can go here 4 times. 2 can go here 3 times. So that this will be equal to 9 over 4 minus 3 over 4 root 3. Since they still have the same denominator, you can now rewrite them at 9 minus 3 root 3 over 4. So this is my final answer for this sword. So that's how to solve swords for rationalization, addition, subtraction, and simplification of swords. If you like the video, leave a thumbs up, share with your friends, and subscribe to the channel. Thanks for watching.